As always, announcements and reminders to get going. Um, Homework 4 is due today, and I know I got the date right this time. It is due today. Um, there's a lot of discussion on Canvas, and it's quite possible that if you have a question, there's already some, not Canvas, on Piazza. And it's probably, your questions might already be addressed if you have any concerns. If not, and you want some last minute clarifications, I have office hours today after class. At 2 p.m. And so we can work on that as well. Other things that are on the horizon, there's a project milestone that's due on Tuesday. We've extended it to Tuesday. And some of you already been submitting it. If you haven't done it already, it's 2 more submissions on Kaggle and another short report. So by the end of this milestone, you should have had at least 3 submissions on Kaggle. Some of you have many more submissions on Kaggle too. And then there's going to be another homework 5, that will show up on Canvas later today. And this will be the last homework for the semester. This will take us, the homework 5 will be due, not the last lecture, but the one before that. I don't want to commit to that yet. Homework 5 will be due on 2 weeks and a few more days. You'll get a little longer than 2 weeks for homework 5. So it'll be due on a Tuesday, even though it's getting released on a Thursday. And it involves you implementing SVM. You will derive and implement logistic regression. We'll cover logistic regression on Tuesday. By the time you come to homework, you'll have enough material. And there'll be an extra credit question involving a neural network that you can choose to do. By the end of homework 5, you will have many different learning algorithms implemented. So as you're doing your homework 5, you can also start using that for your project also. Any questions about any of these things? We are getting closer to the end of the semester. The schedule for the semester is a little bit strange in that the spring break is not in the middle, but closer to the end. So we're getting closer to the end of the semester. And, I just want to kind of point out that one thing that happens at the end of the semester is everything piles up. In this class, definitely things are piling up. So homework 5 will be due in the last week. A project will be due around the same time. And then the midterm, no, not the midterm, there'll be a final exam. All of those things seem to line up in the exact same week. So, since you already know this, please plan ahead. Any questions, concerns? Yes.
I think I saw this on Piazza, but are you guys trying to have the midterm graded by the end of this week?
Yeah, so we're kind of working our way through it. My hope is that it'll be graded by tomorrow. But we are working our way through it. Yes.
For the Kaggle submission, suppose for the first milestone we used the decision tree.
Yes.
And we got an X accuracy. And for the next 2 we used perceptron or
Sure.
But we did not get more than the X accuracy.
That's fine. That's fine. I mean, it's expected, right? I mean, if you use a model that's not as good, you're going to get possibly a worse accuracy, or F1 in this case. But I do want to point out that I'll give you a big hint. Think feature transformations with perceptron. And a certain kind of a feature transformation that you have to, if you look at the data, you'll get a clue. Yes.
Would like perceptron without feature transformations and perceptron with feature transformations be 2 different submissions?
Yes, there would be 2 different submissions. Yep. All right. So today we're going to start a new topic, or at least a topic we've already seen before multiple times, but we're just going to give it a name and consolidate something. We're going to look at this idea that learning can be framed as loss minimization. We've already seen this before. The general setup looks like this. You have some examples, X, that are drawn from some fixed, possibly unknown distribution over the instance space. And then there's a hidden oracle function f that assigns labels to each example. Our goal is to discover a hypothesis H that mimics the f using the data that we have. And in a perfect world, what you could do is you could define some function L that penalizes mistakes that this H makes. And your learning criterion could be find a hypothesis that makes the fewest number of mistakes. It's essentially search over all possible functions to find a function that minimizes this value of L, but really fewest number of mistakes in what? Ideally, we would like to find the hypothesis that minimizes the expected number of mistakes. This is expectation. So let's parse this expression here. You have some example X, f of X is the ground truth, and you have a certain hypothesis, H. H is giving a label to that example as well. And L is a function that takes the prediction H of X and the ground truth f of X and provides a certain score, or rather provides a certain penalty for mistakes. It could just be -1 point if H is not the same as F, or it could be a little bit more nuanced. It could assign partial credit somehow. Either way, we get a number. L of these two things provides a number. What we would like to do is we can compute the expected value of L over all examples drawn from that distribution that we don't have access to. That could be essentially the expected, think of it as the expected penalty assigned to this hypothesis H that we are currently entertaining. Instead of penalty, we can call it the expected loss. This expectation is the expected loss assigned to that hypothesis. And we can frame the problem of learning as simply finding the hypothesis little h inside the hypothesis space capital H that minimizes the expected loss. Does that make sense? Seems like a well-defined strategy until you start to think about how to implement it. Where does this run into trouble? Let me highlight a word that should be a big hint. Or yes.
If you don't know F.
Let's say we know F, or let's say we don't know F, but we have access to an oracle function. You can call F as many times as you want. You don't know the function, but you can call it. But there's still a bigger problem here. This word here. I want to compute expectation over some distribution, but I don't know that distribution. How do you compute an expectation when you do not actually have access to that distribution? The whole agenda falls apart because we are assuming that we can compute this expectation, and then we are assuming we can minimize it. Let's set aside the problem of minimization. Let's make optimization somebody else's problem. We still can't actually compute the expectation. So how do we address that problem? What have we been doing so far? Yes.
Gradient descent on our loss function.
Well, that's answering the question of how to do the minimization, but how do you compute this expectation?
So that the distribution of the same is the same as the other.
So you're sampling. First of all, even forget the same or not. If you do not have access to a distribution, but you want to compute some sort of expected value, an empirically meaningful thing to do is to sample. So instead of the expected distribution, we are minimizing an instead of expected loss, we are minimizing the empirical loss. The empirical loss is nothing but you have a training set. Examples that are sampled from this distribution. We don't have access to that distribution, but nature is kind enough to give us samples from that distribution. And so we have a large training set, and we collect examples, we collect M examples, I calculate the value of the loss of the hypothesis on every single one of those examples, add them up, divide by m, I get the average loss or the empirical loss, which is a sample, which is a estimation of that expectation, even without having access to that distribution itself. So we can calculate the empirical loss on the training set, which is simply the number of points this classifier loses on the training set for making whatever predictions it does. And you find the hypothesis that minimizes the empirical loss. Let's say you can do that. Let's say we use something like gradient descent or some algorithm to do that. What's the problem now? Let's say I can find a classifier that gets 0 empirical loss. That's perfect on the training set. Yes, it can overfit. So if you do that, you might end up finding a hypothesis that's so complex that it fits the noise in the training data. So what we can do is we need something that biases the learner towards hypotheses that do not overfit. This minimization problem needs to be changed slightly. And one way of doing that is to add something called a regularizer. Rather than just minimizing the empirical loss, we have a regularizer which is penalizing complexity and empirical loss that is penalizing mistakes. And we take a weighted sum of these two things. And the job of the learner is to minimize them. This is called regularized loss minimization. Sometimes you also see, instead of the word loss, you also see risk. So we have loss minimization as like a guiding principle for defining learning algorithms. Have you seen this before? Something like this, not exactly this, but something like this. You're nodding. Okay, yes. SVM looks like this, right? SVM has a regularizer that is but basically looks something like this. And a loss function that takes the ground truth, xi and yi, and the weight vector w, and computes some penalty. SVM is a kind of a loss function, or rather, SVM uses a particular kind of a loss function called the hinge loss. Let's talk a little bit more about loss functions. Loss functions should penalize mistakes. And we're minimizing the average loss over the data. Let's say you're training a binary classifier. Your binary classifier can either predict true or false. What should the ideal loss function be? Imagine that you want to minimize the number of mistakes. You remember those true-false questions you had in your midterm? How would you grade those true-false questions? Asking for a friend. Yes.
See if the predict label matches the actual label.
And if it does, how many points would you give or take away?
Just all points.
You'll give all points, and if it does not, you take away 1 point. Or rather, we're talking penalties, right? There's a certain strand of pessimism that seems to run through this whole field. We talk loss minimization and we talk penalties. We don't talk about giving points, but we talk about taking away points. So how many points would you take away for a mistake? Let's say 1 point. And if there's no mistake, you take away 0 points, right? That seems like a reasonable thing to do. Well, that has a name. It's called the 0-1 loss. The 0-1 loss essentially says you have the ground truth y and the prediction y prime. If the prediction and the ground truth do not match, you take away 1 point. The loss is 1. If the prediction and the ground truth do match, then there's no loss. The loss is 0. Seems like a perfectly reasonable thing to do if all you care about is mistakes. With binary classification, with linear classifiers, things get a little bit neater. Your prediction can be written as sine of W transpose X. So this expression here, right, when Y and Y prime are not the same, is equivalent to saying when Y W transpose X is negative. If Y W transpose X is negative, then the loss is 1. If Y W transpose X is positive, then the loss is 0. Importantly, This is a penalty that's assigned to the prediction system, to the classifier. In this case, to the weight vector. This weight vector W is assigned -1 points if it makes a mistake. We don't keep the minus, we're just saying it loses a point if it makes a mistake. The good news is this is exactly the thing that we care about when we are measuring accuracy, because adding up 0, 1 loss over a training data is basic, and dividing by the number of examples is basically accuracy. So 0, 1 loss is a reasonable thing to hope to optimize. The bad news is it turns out minimizing the 0, 1 loss is an intractable problem. It's computationally intractable. So we need to invent surrogates. We need to invent variants of this expression that we can actually optimize using whatever optimizer you have, like gradient descent and such things. And a certain view of machine learning is that I care about minimizing 0, 1 loss. I can't do it. I need to invent surrogates. Let's build a cottage industry that keeps inventing surrogates. So let's look at some surrogates. Actually, we've seen some surrogates. This is the 0, 1 loss. I've plotted here in the horizontal axis. I'm plotting YW transpose X. Vertical axis is the loss. Higher means you're losing more points. If YW transpose X is greater than 0, so on this side, there's no misclassification because Y and W transpose X have the same sign. So there's no penalty, so the loss is 0. If YW transpose X is negative, the loss is 1. Notice that my drawing software is a little bit messy. This should really not exist because we have a step function here. This function is not continuous. It's not continuous, which means we can no longer take derivatives. The whole plan for using stochastic gradient descent falls apart. So we invent surrogates. We've seen some surrogates. One surrogate that we saw was the hinge. The hinge loss says if YW transpose X is more than 1, there's no penalty. If YW transpose X is negative, there is a penalty, and the penalty keeps growing the more negative it gets. And even an example that's predicted correctly but lies within the margin gets a certain penalty. It's not exactly the same shape as that the 0, 1 loss, but it has a similar flavor. And it also has that extra thing that says the more you go in this direction, the more wrong it is because the penalty keeps increasing. That's what this is the hinge loss. In fact, I could have introduced SVM in a completely different way. Instead of introducing SVM as, through margins and we see dimensions and all that, I could have said machine learning is nothing but loss minimization. Let's look at loss number 1, hinge loss. Loss number 2, there are other losses that we'll come to. So, SVM is another way of introducing SVM is to say, I would like to minimize 0, 1 loss, but I can't do it. Instead, I've come up with a surrogate that has a similar flavor. I'm calling it the hinge loss, and it's this expression here. So if I want to kind of ground everything, we've seen this before, but I want to revisit this point in the context of loss minimization. SVM, the objective has a regularizer and an empirical loss. The goal of the regularizer is to push towards better generalization. The goal of empirical loss is to push towards better fitting the data, so to speak. There are other regularizers that exist. There are other loss functions that exist. If you change the regularizer, you don't get new algorithms. You get essentially, this is sometimes this is called just SVM or L2 regularized SVM, because this loss is sometimes called the L2 loss. There is the L1 regularized SVM, which is also called rich. No, that's for regression, so never mind. But there's also L1 SVM, which exists. If you change the loss function, you get other learning algorithms. Both these terms are important in the learning part. And there's a hyperparameter C that controls how important these things, their relative importance. C is a number between 0 to infinity. When C is 0, you're essentially saying, don't fit the data at all. This whole thing disappears. When C is infinity, you're saying, I don't really care about generalization. This term disappears. That doesn't matter at all. The model is forced to overfit the data. And most practical applications involve some C in between. You'll be in your homework, next homework, you'll be finding a value of C through cross-validation. But that's just one particular version of the loss. Turns out there are other kinds of loss functions. There's something called the perceptron loss. The perceptron loss looks very much like the SVM loss. The only difference is it does not have this one. The perceptron loss, if you minimize the perceptron loss, you get the batch version of the perceptron algorithm. We've seen AdaBoost, right? It turns out if your weak classifiers in AdaBoost are just individual features themselves, turns out AdaBoost is minimizing something called the exponential loss. That's another origin story for AdaBoost. Instead of saying that AdaBoost is an algorithm that is boosting weak classifiers, etc., I'm minimizing loss. I care about minimizing 0-1 loss. It's intractable. Instead, I pick an exponential loss and you get AdaBoost. Next Tuesday, we'll be looking at logistic regression, but I'm giving away the punchline today. Logistic regression minimizes the logistic loss, which is just another expression here. Don't worry about the details. You'll know exactly how to derive it, and in your homework, you'll be staring at it more than you'll be happy about. But we'll get to that eventually. I can plot all of these things here. So we have the 0-1 loss, which is in a certain sense what we would like to minimize. There's a hinge loss that SVM minimizes. There's a perceptron loss, which is nothing but a shifted version of the hinge loss. There's the exponential loss, which is what AdaBoost minimizes. There's the logistic loss, which logistic regression minimizes. And I have shown you a zoomed in version of this. If you actually zoom out, it turns out the SVM, logistic regression, and perceptron look very, very similar to each other. If you zoom out, they don't make too many big, two very different decisions. The sort of hand-wavy conclusion from that is, in a perfect world, SVM, logistic regression, and perceptron with a little bit of extra tweak to it, namely through averaging, with the right sets of hyperparameters, if you choose them correctly, they'll perform roughly similarly. Which is kind of a disappointing thing to hear about after going through all this technical complexity. But on the other hand, it turns out there's a nice unification of ideas. So that's pretty much the quick summary of this idea of learning through loss minimization. This agenda is extremely productive. The goal of learning is to not define learning algorithms, but to define loss functions. If you have a certain property that you would like to inject into your learning algorithm, into your learner, or into your model, one way of injecting that property is if you think hard and you can come up with a loss function that captures that property. As long as the loss function is differentiable, you throw it into the loss and you just minimize the loss using some version of gradient-based optimization, and you've invented modern machine learning. This is for SVM and your homework 5 data. It's also a large part of the biggest and the largest models that we encounter today. There is often, for the largest models, there's like an extra layer of learning that happens on top that involves something like reinforcement learning. But to get to that, first they do this sort of thing. They write down a loss function, they minimize it, and what changes is what model do you use, what data do you use. Often you have to regularize to avoid overfitting. Regularization is a standard strategy to avoid overfitting, or alternatively, regularization is a strategy to improve generalization. Regularization is one of the ways to improve generalization. It's not the most common approach used today. It turns out for very, very large models, rather than using a regularizer, a different idea called dropout is used to introduce generalization. We'll look at dropout when we see neural networks. But this idea of loss minimization is very widely applicable. There are different kinds of loss functions that exist. There are different kinds of regularizers that exist that have interesting properties. Some regularizers are data-driven. Some of them are purely geometric. And often when we read papers today, people don't talk about how these things are optimized. We just, even the state of the art papers, they just write down the loss function and say, we minimize this loss function on the data. If you're lucky, you even get an expression for that loss function. Sometimes it's such standard loss functions being used that you'll just see a sentence like, we minimize cross entropy loss on the training data for our optimization. Cross entropy loss is just the multi-class variant of logistic regression, it turns out. And it's a very robust sort of a framework to think about machine learning. Questions? For the 0, 1 loss? So the 0, 1 loss is a discrete function, right? And you're no longer actually solving a continuous optimization problem. You're solving a discrete optimization problem. And it turns out that discrete optimization problems tend to be more messy. I don't want to get into the nitty-gritty of it, but basically the idea becomes you are searching over a large combinatorial space instead of a large real-valued space. And combinatorial search is messy. Other questions? Yes.
So let's take SVM for example. So can we also use like a different regularizer instead of the one?
Yeah, absolutely. So let me show you an example of a regularizer. So the version that we saw looked like half W transpose W plus C times hinge loss, right? This quantity here is nothing but the sum of Wi square, which is nothing but, I'm going to give it a name. It's the L1 norm, L2 norm of W, or the square norm. Alternatively, another thing I could do is, so I can write that compactly as half length of the vector squared, right? Plus this quantity here. Instead of, I put a 2 here because that's the Euclidean norm. I could replace it with a 1 norm, which is nothing but, I'll write it as W1 plus C hinge. And this expression is nothing but the sum of the absolute values of Wi. Both of these have a similar sort of a flavor. Both of them say, in the absence of any information, I would like to push that, let's say that weight Wi has no support for either decision, for a plus or a minus or whatever. Then, in the absence of any information, push that weight to 0. Because you're minimizing Wi square, the minimum value is 0. You're minimizing the absolute value, the minimum value is W. Except because of the geometry of these two, because of certain geometric properties, the L1 regularizer, that's what this is called, tends to push for sparser solutions. So if you care about sparsity in your weights, a natural thing to use is L1. And the good news is, even though you have an absolute value is continuous, and it's not differentiable only in one place. So you can use subgradients. So subgradient descent still applies. And the even more good news is that standard libraries have this baked in. So you don't really have to think too hard about deriving the gradients and all that. So this is just one example. There are other sort of more complicated kinds of loss regularizers that exist, but often the complicated regularizers don't necessarily, you need to justify them. You need to be able to say, for my problem, it has this interesting requirement / property that motivates the need for a certain interesting regularizer. And there are more that exist, which we can talk about if you're interested. Yes.
So we find the best loss function for certain problems.
How do you find the best loss function in practice? The one that you have the most efficient implementation of is the best loss function. Because SVM, logistic regression, and average perceptron behave essentially similarly. These days, a lot of, with the neural network sort of things, the loss function that gets used most often is cross entropy. Cross entropy is the multi-class extension of logistic regression. And one of the reasons it shows up a lot over, for example, multi-class extension of the hinge is because there are efficient implementations of it, and they came up before the other one, hinge, was implemented efficiently. So culturally, there was a shift towards that. And another reason is there's a probabilistic interpretation to that. And if you care about other aspects beyond just accuracy, if you care about your weights producing probabilities in a certain way, and you want it to be natively tuned to that, then you can use cross entropy, which is one of the reasons people use cross entropy a lot. So first criterion, whatever is efficiently implemented. Second criterion, if you have other auxiliary aspects that matter to you. Like, for instance, you want your model to produce